Welcome back to the Algebra 2 series. Today we are going to continue with our inverse functions section, and in part 1 we came across this function here, example 1, where g of x was equal to x plus 1 over 3x minus 2, and in that video we computed g inverse, which turned out to be 2x plus 1, and that was over 3x minus 1. And so today I thought I would go ahead and work through the composite g of g inverse of x. And as we realize in the past, the g of g inverse should turn out to be x when we're finished. Likewise, g inverse of g of x should also equal x. But for today's video, we're just going to do the g of g inverse. If we're going to do g of g inverse, that's the same as g of g inverse of x. In other words, the inner function is g inverse, which implies that we are going to take this function and substitute the entire quantity into both places for x. And if we do that, we will end up with this massive fraction. Instead of an x plus 1, we're just going to get this blob, 2x plus 1 over 3x minus 1, that being g inverse. And then the denominator has a 3, 2x plus 1 over 3x minus 1. And that's going to be minus 2, as you see from this denominator over here. Moving down to the next step, we would like to get rid of that 3x minus 1 in the denominator. And I see there's 1 here, and there's also 1 over here. So if we multiply this fraction by 3x minus 1 over 3x minus 1 and distribute carefully, we should be able to knock out all of those denominators at once. And let's do this with the numerator first. As we multiply the first one, we end up with this 3x minus 1 canceling with the 3x minus 1 outside, leaving just 2x plus 1. And of course, in the second case here, with the 1, we just put plus 1 times 3x minus 1. And down on the bottom, the first time here, we do get a cancellation, leaving the 3 from the outside and the 2x plus 1. And then minus 2 times the 3x minus 1. These are quantities in the top and bottom. Do not cancel them. Obviously, we'd want to just work through this and see how this comes out to be. 2x plus 1 plus 3x minus 1. And this is 6x plus 3 minus 6x plus 2. And then finally, doing the last step here, I get a 5x in the top, the 1's drop out. In the bottom, the 6x's drop out. I'm left with a 5, and that, of course, does turn out to be x. And so we always put a little happy face at the end to show that we were able to establish that the identity was, the inverses were verified. So once again, that's the purpose, is to show that this is going to be verified. And it has to be x. Okay, let's move on to a second problem. And here we have the issue of quadratics not being one-to-one. But notice in our example here of f of x, we have a function that is x squared minus 3, and I'll just graph the part of it that we need to see. If you go down 3 units, but we're restricting the domain to x greater than or equal to 0. So the graph looks like this. This would be a point, and then I believe the point 2, 1 is on this graph. This is our f. Finding the inverse is typical of what we usually do. We write y equals x squared minus 3, and we use our pig's tail. X is equal to y squared minus 3. And we'll solve for y. Here's where we have to be a little bit careful, but not too bad here. X plus 3 is equal to y squared, and solve for y. Y is equal to plus or minus the square root of x plus 3. And that's where the fun begins, right here. This plus or minus. We actually have to determine if it's going to be positive or negative. Well, we can do this by a couple different ways. The first way is to inspect our inverse, and if we have a point at negative 3 on the y-axis, then that'll produce a point negative 3 on the x-axis. And then if we have a point what would that be, about 1, negative 2, then that would be negative 2, 1. And so if we were to reflect our graph over, we would see it should look something like this. This should be our F inverse, which would imply the positive half of that um, parabola, that sideways parabola. I'm going to take this bottom part out. So knowing that, we come back over to this side, and we're going to take out that and just leave the positive square root, or call that F inverse the positive square root of x plus 3. We do not need to put a special domain restriction on that because the domain is automatically restricted on a radical function. Then it also states to verify that the composite yields x. So we're going to do f of f inverse of x, which means take our f inverse and plug it back up in there. That would give me the square root of x plus 3 quantity squared minus 3, or x plus 3 minus 3, and that verifies to x. That's usually very quick work in there. It doesn't state here that we should have the domain and range or the graphs, but that's what the graph would look like, and the domains and ranges do reverse. Now notice that this problem can work both ways. Notice in the second half we have g of x that in this case is the radical problem. So let me do this one similar to what I just did there. This would be radical x move 2 down. Should look something like this. Did I do that properly? Yeah, I did. Okay, so that looks good. And if I were to reflect this one over the y equals x line, it would come out being, and I could actually do this in my head almost, negative 2, and this would go to, this is 1, negative 1 right here. This is 1, negative 1. It would go to negative 1, 1, and the graph would do one of these deals. And then you say, oh, well, what is going on there? Well, that looks like half a parabola. And you could almost write out what this is. This is going to be x minus, excuse me, let me rewrite that. That's not x minus 2. That would be a transformation to the left. So g inverse of x would be x plus 2 squared, moving to the left 2, and then we need to restrict our domain x greater than or equal to negative 2. Well, let's see if that's what happens when we work through the algebra. In this case, y equals negative 2 plus radical x. Flip the x's and the y's. Bring the 2 to the other side. Square both sides. And there's our answer. This is g we're dealing with now. G inverse is equal to x plus 2 quantity squared. Now there's a trick to this problem. The trick is, or I should say the trap, is that we normally would not write this down, x is greater than or equal to negative 2, but it is required here. X is greater than or equal to negative 2 in order to make this graph 1 to 1. We are required to put on that unusual domain restriction on our inverse function this time. Without that domain restriction, we would be graphing the entire function, both sides, and then it wouldn't be 1 to 1. So it would not be the true inverse of our function. And lastly, we're going to verify this. This time I'll do a little, kind of mess us up a little bit, g inverse of g of x. And I'll just do that just for fun. In this case, the g inverse, which we found down here, is going to go into here. And it turns out that the verification looks just like the last problem. Negative 2 plus the square root of x plus 2 quantity squared, negative 2, and in this case it is plus x plus 2. And the reason I don't need an absolute value around this is because of the domain restriction x greater than or equal to negative 2. There's no absolute value necessary there. So the answer comes out to be just x. All right, there you go. A couple of different inverses with the square root and the x squared graphs. So you've got quadratics and radical graphs where their inverses kind of look and work toward each other. And I'm going to stop right there.